Hey everybody, and welcome to the video for chapter 5.1 titled The First Derivative. Now in chapter 5, what we're going to look at, I'm going to give you a function f of x, and we're going to start to analyze important features of that function. So where are their peaks, where are their valleys, when is the function increasing or decreasing, and what happens as we go to infinity or minus infinity. All these different things. The derivative of the function is going to help us analyze those different aspects of a given function. In this video, we're going to focus specifically on the first derivative, and there's going to be three parts. I'm first going to review f prime of x, your first derivative. Then I'm going to introduce in part 2 the concepts of critical points and relative extrema, and then we're going to finish with some examples so you can see how exactly we apply this to different functions. So before we get into the main part of the lecture today, let's review our first derivative. So we call that f prime of x. And there's just a few important things I want to point out. F prime of x, that's just the derivative with respect to x of your function f of x. All right, and we have all sorts of rules to allow us to find that derivative. But what we care about more in this chapter is what that derivative actually represents. So if you evaluate the new function you get for the derivative, if you evaluate it at some point c, this represents, and we can interpret this in two ways. First, it represents the instantaneous rate of change of the function at x equals c. So it gives us some way to tell how f of x is changing exactly when the value x is c. And the other interpretation is a very important interpretation, is that it's the slope of the tangent line to the graph of f of x at your point x equals c. So if I've drawn f of x down here, and you come along and you pick, say, a point c down here, you're going to go on up to the graph, you find that point on the graph, draw your point, and your tangent line is going to be the line that just grazes that graph at that point. This is your tangent line. That's going to have a particular slope, m, and that slope will be exactly equal to f prime of c, the derivative evaluated at c. Now this idea is going to lead to a really important test that allows us to figure out when a graph is increasing or decreasing. So because the first derivative tells us about the slope of the tangent line, anytime that first derivative is bigger than 0, it's positive on an interval, then f must be increasing on that interval. And we've done some examples in the past on this. So for example, up here, on this entire interval from, say, 0 to c, I know that my slopes are positive. Any tangent line you draw here will have a positive slope. So my derivatives are positive, and therefore the graph, if you're in a car, you're driving uphill, you're increasing. All right? And likewise, if you have a negative derivative, then your function is decreasing on that interval. So this is important. You're going to be asked to find intervals for when your function is increasing or decreasing, and we can use the first derivative for that. We've already seen this in some examples in the previous sections. So that brings us to the main dish for our lecture here, and that's discussing these new concepts. And that's part 2 here. The first of these concepts is called relative extrema. Remember, our goal, as I mentioned on the first slide, our goal is to analyze important features of a given graph. So I've drawn a graph down here. And when I say important features, what we really care about, one of the most important things we care about, are your peaks and your valleys. So for example, on this graph here, if I wanted to circle my peaks, I would go ahead and I'd say, yep, there's a peak right here. So there's one of them, and there's another peak right here, kind of a high point on this mountain range per se. And if I took the orange and I said, all right, let's find our valleys. Well, I have a valley down here, I have a valley down here, and I have another valley down here. So when you box off these little points, those are some important features of this graph f of x that I've drawn. Now we care about pretty much where those actually happen. So what's your x value for which that peak happens? What's the x value for which this peak happens, etc., for all of these peaks and valleys? Okay. But in any case, the peaks and valleys, they have special names. Those blue peaks, we call those relative maxima, and the orange valleys we call relative minima. Now there is a formal definition for relative maxima and relative minima, but it really is pictorially easier to understand. It just means that if you put a marble in the area near that relative minima, it's going to come right back down to that minima. So it's smaller than everything around it. So if you took a little neighborhood around it, it's smaller than everything around it. Same with the maxima, it's bigger than everything around it in a little neighborhood. All right. Together, these are called your relative extrema when you take the maxima and the minima together. Now, for the next step of the journey, still in part 2, we're going to introduce a concept called a critical point or a critical value. So suppose that you want to know where the peaks and valleys are for a given function. So we have some function, I want to know where my relative extrema are. But suppose you don't have the graph in front of you, you just have the equation. So you need to have a way to determine where those peaks and valleys might be located. And the critical points are going to help us locate those. All right, so as a definition, we say that a value, x equals c, is a critical value. All right, the point would be the ordered pair associated with that, but if you're just talking about the x value, it's a critical value for the function f of x if two things are satisfied. First of all, it has to be in the domain of the function, so it can't be a point of discontinuity of the function. And second, the derivative at that point, c, is 0 or doesn't exist. All right, and why is that? Well, let's draw some peaks and valleys, some potential peaks and valleys. So, for example, I could have a valley that looks like this, or I could have a peak that looks like this. I could also have a valley that looks like this, or a peak that looks like this. Okay. Now, if I zoom in on the point where I have either the peak or the valley, notice that. So this would be kind of your point C. Notice that in the first situation, the tangent line has a slope of 0. So m equals 0 shows us that the derivative actually is 0 at that point, and there is a relative extrema there. And notice same with this peak. But so the slope is 0 at that point. Here, the slope does not exist. The tangent line does not exist. That's a point that is not differentiable. All right, so what the critical values are doing is they're showing us where these extrema might occur. So it's really important for us to be able to find the critical values in order to then find our relative extrema. That's the main goal. And let's do a quick example here for actually finding these critical values. If I've drawn this function f of x, and you can see it here, if I just said find all your critical values, well, critical values are the points where the points are in the domain where my tangent line is 0 or my derivative doesn't exist. So first of all, I have a point right here because that's going to have a tangent line of 0. So whatever this point is, we'll call that x1. That's going to be 1 point. I also have a point here. That's got a horizontal tangent line there. It kind of levels off at that point. This will be a second critical value, x2. All right. I have another point where I have a horizontal tangent line. So this will be a point x3. Right, and when I say horizontal tangent line, if you were to draw the tangent line, you're going to get a slope of 0 at all three of those points that I've just highlighted. I then have a sharp point. That's a point of non-differentiability. So that's point x4. That's another critical value. And then another point here, x5. It's basically highlighting all of those peaks and valleys, and x6, and also all of the sharp points. But the big thing I wanted to point out here is that you can have critical values where your slope is 0 such that you don't have a relative extrema. And that's going to be a very big source of confusion. And it's a common problem that a lot of students make when they're talking about critical values and relative extrema. So we'll highlight that in some of the examples moving forward. So now the main question becomes, if I know where my critical values are, how can I determine if there's a relative extrema at those critical values? And the answer lies in what we call the first derivative test. This test will help us determine when a given critical value, which we're going to find, it'll help us determine when that value is the location of a relative min, a relative max, or it might be neither. Okay? Now, I know there's a lot of words as part of this test, but once we look at the words, I'm going to show you kind of with pictures and it'll make a lot more sense. So suppose f is defined on some interval and c is a critical value. So remember, that's a value for which the derivative is 0 or the derivative doesn't exist. There's 3 situations. So there's 3 cases that I can have. First, if the derivative is positive near and to the left of your point C, meaning your car is going uphill to the left of your critical value, and it's negative after, meaning you're going to go downhill after, that means you have a relative max at that point, okay? If the derivative is negative before, so you're going downhill before, so that's to the left, and you're going uphill to the right, that means you have a relative min. That should all make sense. And if the sign is the same, so if you either are continuing to climb or continuing to descend, then you don't have a relative extrema. Let's look at what this means in pictures. So I'm going to take this, let's zoom out with our first derivative test, and I want to actually see exactly what this means pictorially. So this first case, if you wanted to have a relative maxima at a point C, so here's your x-axis, what could happen is to the left of C you have a function that's increasing, and then to the right of C you're decreasing. So this is a relative max at that point. And I know that f prime on the right is positive, so you have positive slopes since you're going up, and f prime on the right of C is negative, and that means you're coming down. So at my point C, I have a relative extreme value at that point. You can do the same thing for relative minima. All right, so again, let's draw my x-axis. Here's my point C, and if my function f looked like this, you'll notice that to the left of C, your derivatives are negative because it's coming downhill. So you're traveling down the hill with your car. To the right of C, they're all positive. So you're going up the hill with your car. And so therefore, at that point, f of C, we have a relative minima. All right, and finally, the last case, when I do not have an extrema, this would be if, for example, at C, if it leveled off, so I did have a critical value, but it continued to climb. So you'll notice that f prime, if you think about the derivative, to the left of C it's positive because you're climbing. To the right of C it's still positive because you're still climbing uphill. So we have no extrema there. And you can do the same thing if it was going downhill. All right. This idea we're going to use in a bunch of examples, so you'll see it kind of how we're going to use it in practice. And on the next slide, I'll explain all the different things that we need to think about as we go through this whole process. All right, now we can see how these concepts are applied to some examples. So in these examples, you're going to be asked a few things. You'll be asked to find all critical values. You'll be asked to find intervals on which the function is increasing or decreasing. And you'll be also asked to find all relative extrema for a given function. So I have a procedure that I want to follow. We'll do these 4 steps every time. Your first step, you need to find f prime of x unless it was given to you. Second step, you have to find all of your critical values and your points of discontinuity. Those points of discontinuity are actually going to be really important for us because they'll tell us when we have an asymptote or something crazy going on like that. Next, we're going to put all those values, the critical values and the points of discontinuity, on a number line. So we're going to work purely on a number line. And the final step will be to determine the sign of the derivative on each of the intervals that we've created on that number line. So that'll tell me whether when the function's going up, when it's going down, and I can start to get a sense of the roller coaster ride that function is following. Once we get a sense of that ride, we'll be able to target those relative maxima and the relative minima in order to get our extrema. You'll see this on the next slide. So for our first example, I'm going to call this our type 1 example. And this is when we're given the graph of the function f of x. And so notice the instructions. These are going to be the same instructions for all of the examples we'll do in this video. And they say, for this function, let's find all critical values, let's find the intervals on which it's increasing and decreasing, and let's find the x-coordinates of all relative maxima and relative minima. So when I'm given the graph of f of x, the procedure that I talked about on the previous slide is not entirely necessary because the answer is just staring at us. So for example, let's talk about critical values. Well, you're going to go through and you're going to find all values, and sorry, I need to label my x-axis. So you're going to go through, you're going to find all values where the derivative is 0, so this tangent line is 0, or where the derivative doesn't exist. So I'm going to take my orange pen here. I know that I have a point here, so this is going to be one of my critical values. I have a point here that has a slope of 0 for the tangent line, so this will be one of my critical values. I have a point of non-differentiability there because it's a sharp point, so that'll be a critical value. I have a leveling off point here, so 6 will be a critical value, and that's it. All right, so my critical values, when I'm actually listing my critical values, they'll be the points x equal to -1, 2, 5, and 6. Those will be my critical values. That's the first part of the problem. The second part, let's find all intervals on which f of x is increasing. So that means where on the graph can you get in your car and drive uphill? Okay, so I know I can do it there, and I know I can also do it here. So when we're talking about increasing for the function f of x, we're going to start, our interval will start from -1 and it'll go all the way to 2. That's the interval for my first car right here. Then the next interval is going to start at 5, and that's going to take me all the way to infinity, because this car over here is going to be traveling uphill on that entire interval. And so all you need to do is combine these together and take a union, and those will be the intervals on which your function f is increasing. All right, you can do the same exact thing for decreasing. With decreasing, I'll look for where my car is actually going to be going downhill. So it's going to be going downhill on that segment and also on that segment. And as you express those in interval notation, it'll look as follows: -infinity to -1, union with 2 through 5. Okay. And the final question says, where are my relative maxima and my relative minima? So when I zoom in on my critical points, essentially, let's start with this critical point. When I zoom in on that, it is smaller than everything around it, so that is a relative min. So I will have a relative minima at the following points, at x equals -1. I'll also have one at x equal to 5. That's also a relative min. So it's smaller than everything relative around it, relative to it. My other critical points, I'll have a relative maxima. So if I zoom in on my critical points, I'm going to have a relative maxima at x equals 2. All right. And notice that the critical point x equals 6 is neither a maxima or a minima. So I only have these 2 relative minima and 1 relative maximum. All right, and this answers all 4 parts of the question that we were asked. So when you're given the graph of f of x, it is a relatively straightforward question, but be careful because you won't always be given the graph of f of x, as we're going to see in the next example. All right, so now we're going to look at the exact same question, but we're going to do this for type 2, where I'm just going to be given the function and not the graph. But you can notice the same exact question statement. So now off to the right here, I've written our procedure. This is going to be our main procedure for going about questions like this. So I have the function here. Step 1 is to find the derivative. Now we should all be pretty quick with this using our power rules and all of our other rules of derivatives. So we'll get 21x to the 6th plus 84x to the 5th plus 0. All right, so that's our derivative. Now, step 2 says to find all critical values and points of discontinuity. So for points of discontinuity, you look back at the original function and you say, okay, are there any points that make this discontinuous? And there are none. For our critical values, there's 2 categories for which I have critical values. The first is that the derivative does not exist, and there's no points that satisfy that. And the second for critical values are when the derivative is equal to 0. Okay, so we do have to do a little bit of work for finding when the derivative is equal to 0. We're going to set the derivative we've got from the last step equal to 0. So that's 21x to the 6th plus 84x to the 5th. We're going to set that equal to 0. And the key here, we now want to solve for x. And this becomes an algebra problem. So we're going to factor out 21x to the 5th. And what you're left with is x plus 4. Okay. And in doing so, you're going to find that x equals 0 and x equals minus 4 are my two critical values, because those will make my derivative 0. And that's where the slope of the tangent line will be 0. So for critical values, you get the points 0 and minus 4. So those are the potential places where I could have relative extrema. Now for step 3, we have to determine if there are relative extrema at our critical values. So the way that we do this is we draw a number line. So imagine this as your x-axis. And I'm going to take my critical values and place them on my number line. All right. In doing so, what you've created are 3 intervals. You've got from minus infinity to minus 4. You've got from minus 4 to 0. And you've got from 0 to infinity. So there's 3 intervals. On each of these intervals, the derivative will either be positive, negative, so it's either going to be increasing or decreasing. So what you're going to do for each of these intervals is you're going to choose a test point. So on my green interval, I'm going to choose a point from that interval. So I'm going to pick minus 5. From the next interval, I'm going to pick minus 1. That's something in the blue. And for my third interval, I'm going to pick 1. You really want to pick easy numbers to work with because we're going to have to evaluate the derivative at these numbers. So the next step is you're going to test f prime at these values. So I'm going to actually find f prime at each of these test points. And the idea is that if f prime is positive, then your function's increasing. If it's negative, then it's decreasing. So when you input minus 5 into the back into the derivative, so we're going back right up here to the derivative, when we input minus 5, you're going to find that this is positive. So that's positive. When you input minus 1, you're going to find that this is negative. And when you input 1, you're going to find that this is positive. So again, you can find those values and determine if they're positive or negative. What that means on the number line is that the function over here, I'm going to put pluses because the derivative's positive. Here they're minuses because the derivative's negative. And then here they're pluses again because the derivative is positive. So what this means is that on the green interval, your function is increasing. So it's going to look like this. This is f of x. It's increasing. Then on the blue interval, it's decreasing. All right, on the blue interval, we're decreasing as we go towards 0. And then as we go from 0 to infinity, we're increasing. So what's going to happen at that point? There's an extrema. And you'll notice, so these are our critical values. At minus 4, we have a maximum because it goes up to the high point of a mountain. And at 0, you have a critical value, which is a minimum because you have reached a low point here at a minimum. So what that allows us to do is conclude that, okay, we have a relative max at x equals minus 4, and I have a relative min at x equals 0. And those are your relative extrema. So we found the x-coordinates of our relative extrema. And again, the process is to determine what the sign of your derivative is on each of the intervals that you've split your real number line into. And then if it's increasing, changing to decreasing, that means you've reached the top of a hill. If you're decreasing and then change to increasing, you've reached the bottom of a valley. And you can find your extrema that way. And the final step is to determine when f is increasing. So we want intervals for increasing and decreasing. Well, when f is increasing, that's when you see these pluses. So that's on the green interval and on the red interval. So our intervals will be minus infinity to minus 4, union with 0 to infinity. Those are my increasing intervals, and f will be decreasing on the interval from minus 4 to 0. All right, and those are our intervals of increasing and decreasing. Now you can check out a graph of this function. So you could take this function, graph it in Desmos, and you will see that you'll have a max, a min, and these are going to be your intervals of increasing and decreasing. That leads us to the third type of question you can see here. Again, it's the same exact question, but the third type is when I'm given the function f prime. So we're trying to determine stuff about f, about the actual function f of x, but I'm given its derivative f prime of x. So I don't know what the original function was, but I know what its derivative is. So that can be a little bit confusing right away. In any case, let's do the same computations. So step 1 is to find f prime. Well, you already have f prime, so we are done. F prime is just, it's given to us, okay? So this allows us to actually skip step 2, all right? No, skip step 1. Sorry about that. So step 2, we are going to find all critical values and all points of discontinuity. Now, right off the bat, points of discontinuity, that would be for the original function f of x. And since we're given f prime of x, it's hard for us to determine this. So there are none here, and in this context, we will be told if there are any. So that'll be extra information given in the problem statement. For the critical values, remember there's 2 types of critical values. Either f prime of x does not exist, and there are no points for which this happens because f prime is a nice function. And the other case is that f prime of x equals 0 for my critical values. So we do have cases of that type. So you're going to set the derivative equal to 0. All right. And you're going to look for the points for which this becomes 0. So you have x equals 1, x equals minus 4, and x equals 4. And those are your critical values, so I'll circle that in orange here. These are my critical values. All right. That's the end of step 2. Step 3 and 4, we're going to do these together as we did last time. We're going to take a number line, and we're going to put our critical values on the number line. So in this case, we have minus 4, we have 1, and we have 4. Okay. Now this divides my number line into 4 intervals. On each of these intervals, we want to determine the sign of f prime so that we can determine whether the function's going up, down, or neither. So on the interval from minus infinity to minus 4, pick a test point. I'm going to pick, say, minus 5. And we want to find if f prime of x is positive, negative, or it won't be 0 because they're not critical values. So what we're going to do, what you effectively do is you take this derivative. So I'm gonna circle this derivative right here. We take this derivative and think about bringing that right on over here, okay? And we're going to be inputting minus 5, the value x equals minus 5, into this, this, and this. Now, we could just find a number. It would be some big number. That'd be great. But it's actually easier for us to think about the sign of this. So if I put a minus 5 into this first term, I'll have a negative raised to an odd power, which will give me a negative value. If I put negative 5 into this value, negative 5 plus 4 is negative. When I square it, it'll be positive. And when I put a negative 5 in here, I'll get negative 9 raised to the third. So that's to an odd power, so that'll end up being negative as well. And when you multiply a negative by a positive by a negative, you'll get something that's positive. So f prime of x on this interval is positive, okay? Because I took my test point from that interval and we found that it's positive. Now you'll do the same thing for the other 3 intervals. So pick a test point. Always pick 0 if you can. So again, you're going to look at f prime of x. You're going to take 0 and input it into f prime of x. So I'll get a negative here, you get a positive here, and a negative here. So negative times negative would be a positive. So it's still positive on this interval. Take a test point from our next interval. I'll take x equals 2, and from the last interval, you'll get x equals 5. And you're going to go through that exact process again. So this will be bigger than 0. And when you take those test points, you plug them into f prime, you're going to get negative on this interval, and you'll get positive on the last interval. Okay. So now we draw our conclusions. So that there's nothing happening at minus 4 because you have positives on both sides. You're still climbing. We're going to climb on the left of 1, and then we descend on the right of it. So that's going to be a maxima at this critical point of 1. So that's cool. And then we are descending, and then we turn to be ascending. So we'll have a minima at the critical value x equals 4. Okay, so we can write that on the side here. And then finally, all you need to do is explain when you're increasing and when you're decreasing. You're increasing whenever you see positive derivatives. So from minus infinity to minus 4, then from minus 4 to 1, and then again from 4 to infinity. That'll be when we have positive derivatives. That'll be an increasing function, and decreasing from 1 to 4. So now we have a lot of information about f of x. We kind of can almost go to the next step. And so we've answered the problem, but we can go to the next step and sketch, get a good sense of what's happening with f of x, at least locally. At 1, it's going to have a maximum. At 4, it's going to have a minimum. So we do know that it's going to come up to a max, it's going to come down to a min, it's going to go off like this, and then at minus 4, it's a critical value, so it must kind of level off there but continue to decrease. So this would be a picture of our f of x, and this is going to be where we're going once we finish this analysis. And finally, we're going to conclude this video with example 4. This is the fourth type that you're going to see of these same exact examples. I'm asking for the same thing: critical values, intervals on which the function is increasing, decreasing, and the relative extrema. Now this time, we're going to be given the graph of the derivative. So again, I still want to know information about the original function f of x, but you're given the graph of the derivative f prime of x. This can be super confusing. I find this to be the hardest for students to grasp, so let's try to work through this together. The procedure that I outlined, you can still follow that. In terms of finding f prime of x, well, we already have f prime of x, so we don't have to worry so much about finding it. It's right in front of us. It's drawn. It's graphical. So to find the critical values, you're going to look for points at which f prime of x is 0. Okay, because that's where the tangent line will be 0 for the original function. Now, a lot of people would go and say, oh, my critical values are right here at my peaks and valleys and my leveling off points. That's actually incorrect, because this is the graph of f prime, not of f. So your critical values on this graph are where the derivative is 0. So it's where it crosses the x-axis. So I have critical values, x equals minus 1, 1, and 4. You also have critical values when your derivative does not exist, but there are none of those here. So when we're talking about critical values, we look for when that derivative is 0, and we're given the derivative. So that's step 1. Points of discontinuity, again, that'd be for your original function. We'd have to be told what those are when we're given the derivative, so we don't have to worry about that. Now for step 3, we're going to put all these things on a number line. And actually, I want to move things around a little bit. So let me pause and move this around so I can make my number line right under the function. So here I've drawn my x-axis right under the graph of f prime of x, and I've highlighted my 3 critical points, my minus 1, my 1, and my 4. All right. And now remember, the next step is to highlight when the derivative is positive and when it's negative. So again, this is the derivative, so we can't put a car on this graph and think about when it's heading downhill. That's not going to help us, because that's for the original function. What we care about is when is it positive above the x-axis and negative below the x-axis. Okay? So the derivative to the left on this interval from minus infinity to minus 1, you go on up to your part of your function up here, and that's above the x-axis, so those are all positive. From minus 1 to 1, you go on up to your function, you look at those values. Those are all negative. They're below the x-axis, so that's when the derivative is negative. For the next interval, from 1 to 4, we want to know the sign of f prime. So we come on up to our function. So for these values, those are all positive since the derivative is above the x-axis. So those are positive derivatives. And finally, these will be negative because this portion of the graph is below the x-axis. Okay? So again, we're looking at the derivative, not at the original function. So what this tells us is that on the original function, you would have to have been climbing here, descending there. So you will get a maxima at this point. Then you would be descending here, climbing again there. So you'll get a minima at this point. Then this would be climbing, descending. So you'll get another maxima at 4. Okay? So finally, you can highlight what we have: relative maxima at the points x equals -1 and 4. And we have a relative minima at x equals 1. And then finally, f is increasing whenever your derivative is positive. So that'd be on the intervals from -infinity to -1 union with 1 to 4. And then f would be decreasing whenever your derivative is negative, it's a negative value, and that'd only be from -1 to 1 union with 4 to infinity. Okay? This is the fourth type of example you'll see. And again, I think this is the most confusing for a lot of students, because you're looking at a graph and you're trying to decipher what the original function looked like based off of features from the derivative. Okay? Okay, so I know this was a lot of material and the examples were long and the video was pretty long, but I want to highlight a few things. We have some function, some f of x, some mystical function, and we want to know important stuff about it, right? So where are the peaks, where are the valleys, all this type of stuff. We're using the derivative as a tool to help us locate the peaks and the valleys of a given function. The relative extrema, we want to locate them. The critical values tell us where those are. So our whole process involves taking the function, finding critical values, and then using some analysis and some techniques to determine if I have a max or a min or nothing at that point. Please practice this. Again, there were 4 types of examples we went through. Given the graph of f of x, given the f of x itself as a function, given the graph of f prime of x, and given f prime of x as a function. So please practice all 4 of those types, and I'll see you in chapter 5.2.